Hi all, welcome again to MACM 101 Discrete Mathematics Tutorial 3. In the first two tutorials, we talked about propositional logic, laws of logic, and rules of inference. And in this tutorial, we will cover predicates and quantifiers. So without further ado, let's get to the questions. The first question says, consider the universe of all polygons with 3 or 4 sides and define the following predicates for this universe. So we are given a bunch of statements where like a of x is the interior angles of x are equal and so on. Now we are supposed to translate each of the following statements into an English sentence and determine whether the statement is true or false. So one thing which we need to identify here is that there are two types of quantifiers. One is the universal quantifier, and the other one is the existential quantifier. So the universal quantifier means every element that is present in that universe, and the existential quantifier means that you will be able to find some element in that universe which holds true for your equation. So let's start with the first. It says for all x, q of x XOR t of x. So XOR means that either one of them has to be true, but they both cannot be true at the same time and they both cannot be false as well. So one thing of these has to be true. Q of x reads x is a quadrilateral and t of x reads x is a triangle. So when converted to English, it would read every polygon. This every comes from the universal quantifier. So it says every polygon is a quadrilateral or a triangle, but not both. So being a quadrilateral, it is the q of x, and being the triangle, it's the t of x. And the condition which says it's not both, it comes from the XOR. We'll get to the part of deciding these statements to be true or false later on. First, let's write all of them in English. The second statement is for some x, t of x and p of x. Now, t of x says t of x is a triangle, and p of x says x has an interior angle that exceeds 180 degrees. So that would mean there exists a triangle with an interior angle that exceeds 180 degrees. The third part, again, we have an existential quantifier. It says for some x, q of x and not r of x. Now, r of x was x is a rectangle, so not means it's not a rectangle. Therefore, the statement would be there exists a quadrilateral which is not a rectangle. Part D says for all x, h of x implies e of x. Now, this implication can also be written as if and then. So, if h of x, then e of x. And it would translate to if all sides of polygon are equal, which is h of x, then the polynomial is an equilateral triangle, which is the e of x. Now for the last part, it says for all x, s of x, biconditional a of x and h of x. Biconditional translates to if and only if. So your whole statement would become a polygon is a square if and only if all of its interior angles are equal and all of its sides are equal. E of x is the interior angles and h of x is the sides being equal. So these were all the 5 statements which are converted into English sentences. Now let's see whether they are true or false. So for the first statement, which says every polygon is a quadrilateral or a triangle, but not both, the statement at first seems to be false because uh, a polygon could have more than 4 sides, so it could be anything. It could be a hexagon or an octagon. It doesn't necessarily have to be quadrilateral or a triangle. But if we look at the first sentence, it says, consider the universe of all polygons with 3 or 4 sides. So we are restricted to polygons with 3 or 4 sides. Hence, it could either be a triangle or a quadrilateral, but it cannot be both because it could either have 3 sides or it could have 4 sides. So this statement is true. Moving on to the next, it says, there exists a triangle with an interior angle that exceeds 180 degrees. We know this is not possible. A triangle cannot have uh, more than 180 degrees of any of its 2 sides. That means this part is false. For the third, we have there exists a quadrilateral which is not a rectangle. Again, this is true because a quadrilateral could be a trapezoid. It does not have to be all 90 degrees. So it's true. For part D, we have if all sides of polygon are equal, then the polygon is an equilateral triangle. But since our universe has polygons of 3 or 4 sides, so if your polygon had 4 sides, and since all the sides were equal, it will become a square. Hence, this is false. The last part is a polygon is a square if and only if all of its interior angles are equal and all of its sides are equal. Again, if we had an equilateral triangle, it will have all the equal sides and the angles would be 60 degrees each. Therefore, this is false as well. So this was our first question. Moving on to the second, we have let P of xy and Q of xy denote the following predicates. The first one we have is P of xy is x squared greater than equal to y, and Q of xy is x plus 2 is strictly less than y. If the universe for each of x and y consists of all real numbers, determine the truth value for each of the following statements. The first one being P of minus 3, 8 and Q of 1, 3. So minus 3 and 8 would be minus 3 squared greater than equal to 8, and Q of 1, 3 would be 1 plus 2 less than 3. So clearly 3 squared is 9, which is greater than or equal to 8. It's true, but 3 is not less than 3. It's false. So true and false, the answer would come out to be false. For the second part, we have P of 1 by 2, 1 by 3, or negation of Q minus 2, minus 3. So 1 by 2 square should be greater than equal to 1 by 3 as per the definition of P. And for Q, we have minus 2 plus 2 And now since we had negation of q, it will be, the signs would come out to be reversed. So instead of less than y, it would read greater than y. So it should be greater than -3. Now on the left side, we have 1 by 2 square, which is 1 by 4. So 1 by 4 is clearly less than 1 by 3. It is false. And -2 plus 2, which is 0, is greater than -3. So it's true. Now, since there was or, we only needed one of these to be true. So the answer is true. For part C, we have P of 1, 2 bidirectional negation Q1, 2. So it would be 1 square is greater than equal to true. Bidirectional 1 plus 2 is greater than 2. So 1 square is clearly not greater than equal to 2, so it's false. And 1 plus 2, which is 3, is greater than 2. But since it's a biconditional, both of them have to be true in order for the end result to be true. So this is false. Now moving on to the question 3, we have let Px, Qx, and Rx denote the following predicates. Px being an equation which is x squared minus 8x plus 15 equals 0. Qx says x is odd and Rx says x is greater than 0. Now, if the universe for x consists of all integers, so all integers is an important point here, determine the truth value for each of the following statements. If a statement is false, give a counterexample. Now, before we move on, let's first solve p of x because it's a quadratic equation. We can easily find the solutions to it. It turns out it can be written as x minus 3 times x minus 5 equals 0. So the solutions are x is either 3 or x is equal to 5. So the first one says for all x, px implies qx, which is if p of x, then q of x. So if you have an x that solves p of x, it would also solve q of x. So there are only two x's which fit in p of x, which is 3 and 5. And since q says x is odd, and both of these x, 3 and 5, they are odd. So this basically holds true. So for all x which satisfy px, they also satisfy q of x. Hence, part A is true. Part B says for some x, p of x implies q of x. Now, in the first part, we had for all x which satisfy px. Now we have if there would be some x which satisfy px and then it satisfies qx. And it's basically true because since your whole universe is true, your existential quantifiers are also true. Part C says for some x, Rx implies Px, or if Rx, then Px. So you need to identify there would be some x which is greater than 0 and it satisfies P of x, which is true because pick either of these two x's, either 3 or 5, they're both greater than 0 and they fit P of x. For part D, it says for all x, Px or Qx. then r of x. So the number have to be either satisfying p of x, the equation, or it has to be an odd, then it is greater than 0. This is false because if we have a negative odd number, it satisfies the if condition, but it does not satisfy the then part. So x is equal to -3 will satisfy your left hand side, but since it's not greater than 0, it does not satisfy the right. Moving on to question 4, it says write the negation of each of the following statements as an English sentence without the symbolic notation. The universe consists of all the students at the university where Professor Lenhart teaches. Part A says every student in Professor Lenhart's C++ class is majoring in computer science or mathematics. Part B says at least one student in Professor Lenhart's C++ class is a history major. So let's write them in terms of symbolic notation. P of x would mean majoring in CS, Q of x would mean majoring in mathematics, and R of x means majoring in history. Now, it will be easier if we first convert them into their symbolic notation, get the negation, and then convert it back to English. So the first part, every student in his class would mean for all x, they are either majoring in computer science or mathematics. So P of x or Q of x. Now we take its negation. So not of for all x, px or qx. And upon simplification, it becomes, so for all x becomes for some x. So your universal quantifier becomes existential and vice versa. So for some x, not px and not qx. So its English sentence would look something like this. There exists at least one student in Professor Lenhart's C++ class who is not majoring in CS and mathematics. Now, we could do it in another way as well, since they said X is the universe of uh, students at the university. So we are not here, we didn't consider that they are enrolled in Lenhart's class. So we could add that as well, but this interpretation is fine too. Moving on to the second part, which was at least one student in Professor Lenhart's C++ class is a history major. Now, they are not talking about every student, it's at least one, which means it is an existential quantifier. So it would be for some x, r of x. And its negation would be not of sum of x, r of x, and when you open the braces, your existential becomes a universal quantifier, and it is for all x, not r of x. And the English sentence would be no student in Professor Lenhart's C++ class is a history major. This can also be verified through the question. It says at least one student is a history major in his class. So if I was to ask you what's the opposite of it, so it's pretty evident in this one. It would just be no student in his class is a history major. And that's it for the fourth question. Moving on to the fifth, we have negate and simplify each of the following. The first one is for all x, px implies q of x. And the second one is for some x, px or qx implies r of x. So negating the first one, it's not for all x, px implies qx. Opening the outer braces and taking the negation sign inside, your universal quantifier becomes existential, and it is for some x, not px implies qx. Here we use the definition of implication. So p implies q becomes not p or q. So here it is for some x, not of not px or qx. And opening all the braces, it becomes for some x, px, and not qx. For part B, we have negation of for some x, px or qx implies r of x. Now again, opening the outer braces, your existential quantifier would become the universal quantifier, and it is for all x, not of, I am just using the definition of implication again. It would be not of px or qx, because that was on the left side of your implication, and or rx. So the first two negations cancel out each other, and your disjunction becomes conjunction. So it would be for all x, px or qx, and not r of x. And that's it. Moving on to question 6, we have determine the truth value of each statement in the case when the universe comprises of all non-zero integers, and in the case when the universe consists of all non-zero real numbers. Now here we have two questions. One is about non-zero integers and the other one is about non-zero real numbers. So for the first part, we have for some x, for all y, xy equals 1. Now here's the thing. When your quantifiers are not the same, the order matters. The left side says for all x, there's a y which satisfies the equation. But the right hand side means for a particular y, you could have all the values in the universe for x and it would still satisfy the equation. We could see this with an example. So if we have a function loves x comma y, so the one on the left would very plausibly says that everyone loves someone, but it allows for the possibility that different people have different likes. But the one on the right, however, says something completely different. It says that there is at least one person who is well loved by everyone, which is clearly not the same thing. So, as per our question, we have for some x, for all y, xy equals 1. So, it would be there exists a non zero integer x for which xy is 1 for all the choices of non zero integer y. Now, xy equals 1 is a hyperbola and it has infinite solutions, but for every x, there is only one y which satisfy this. So there does not exist some x for which no matter what value of y you choose, it's 1. So this one is false. And here we were talking about integers. The next part would be for real numbers, but again, the answers are still the same. So even if you have integers or real numbers, in this particular case, it still has unique solution for every x. That means you cannot have more than one y for each value of x that you choose. The second part is for all x, there is some y which satisfies these two equations at the same time. 2x plus y equals 5 and x minus 3y equals minus 8. So for integers, it will be for all non-zero integer x, there exists a non-zero integer y such that 2x plus y is equal to 5 and x minus 3y equals minus 8. Now, since these are linear equations in two variables and we have two of them, that means there would be one unique solution. Solving these two equations gives us x equals 1 and y equals 3. Now, since we don't have a solution for all non-zero integer x, that's why this part is false. And for the second part, we have for all non-zero real numbers x, there exists a non-zero real number y such that these two equations are satisfied. Again, since we have just one unique solution to both these equations, it does not matter whether it's an integer or a real number. If I could pick any x other than x equals 1, it won't satisfy these two equations. It could satisfy one of them, but then we will not find a solution to the other. That's why this is false as well. Now, moving on to the last question for this tutorial, we have let the universe for the variables in the following statements consists of all real numbers. In each case, negate and simplify the given statement. So it's pretty straightforward. We just have to do the negation and then then simplify it. So in the first one, your universal quantifiers become existential. So we have for some x, for some y, not. So this is the negation that was brought in. Uh, and in the brackets, we are opening using the definition of implication that gives me not of x less than y or some z x less than y less than z. Taking this negation inside, uh, these two negations cancel out and gives me x less than y. Your disjunction becomes a conjunction. For some becomes for all, so it would be for all z. Now, since it was x less than z and z less than y, it would be the other way around, and it would be x is greater than or equal to z, or z is greater than or equal to y. You could think of it as splitting these three inequalities into two. So the first one would be x less than z and z less than y. So the reverse is x greater than equal to z or z greater than equal to y. For part B, we have for all x, for all y, x greater than 0 and y greater than 0 implies for some z, x times z is greater than y. Now, in questions like these, you have to take care of where the position of the brackets is. Like in this is one part, and after the implication is another. So when you open the implication, uh, it would be not of the whole left side, which is for all x, for all y, x greater than 0 and y greater than 0, or not z of xz greater than y. Taking the negation of the whole statement inside, uh, the first two negations cancel out, and it leaves me with for all x, for all y, x greater than 0 and y greater than 0. Now your disjunction becomes a conjunction, existential becomes universal quantifier. It is for all z. Now your inequalities are also reversed. So instead of xz greater than y, it will be x times z is less than y. That's all we had for this tutorial. See you guys next week.